con el año 2021 DUNCAN. Si vemos acá, recién nos traen las publicaciones de DUNCAN, están en rangos de alto impacto, tanto en Seminario como en el cuartillo, en la unidad de la productividad, ¿no? Y para repasar un poquito lo que es en sí la trayectoria de DUNCAN, la siguiente lámina nos muestra algunas cosas que uno aprende cuando realiza los currículos de la persona. Él es bachelor en matemáticas y física, y en ambos casos honor de la Universidad de Waterloo en Canadá. Su máster en el 2004 y su doctorado también en matemáticas aplicadas desde el año 2007. De ahí se traslada a DUNCAN a Europa, ¿verdad? Y entonces empieza a trabajar con Atomic Material Design en la Universidad de Dinamarca y con su doctorado hasta en el año 2010 se mueve a la facilidad de espectroscopía física en la bella ciudad de Nanosca, la bella ciudad de San Sebastián. Ahí trabaja en el virtual paper de DUNCAN de esa etapa, ¿no? Está con nosotros desde el año 2016, donde empieza como profesor asociado y en el curso que participó era el curso y simultáneamente profesor adjunto en la Universidad de Guatemala. DUNCAN tiene un agente y uno de los índices más altos que tenemos hoy en la universidad, de 28,85 artículos en el Corpus y 114 registrados en el curso, del cual le da un índice de 32 y un 10, la posición de ese índice de 54, muy, digamos, impresionante. De acuerdo al ranking que tenemos de este índice, creo que es el último, el 2022, el DUNCAN tiene la posición 30 y 57 entre los científicos del Ecuador. Me siento sumamente nuestra dirección se siente muy orgullosa de presentar a DUNCAN en el día de hoy. Estamos repitiendo por el cine, así que esperamos a la disciplina. Adelante, the project now it's in English. Okay. So, whatever reason this detail is a bit small in the image, you have trouble seeing the bit closer. I go trajectory. That's something that's the baseline I like that when their options of that. And so this includes things like random spectroscopy. So this is this is the single wall or the nanotube and the really low where this, okay, and this work was done with Professor Jekyll, where he was developing with the acid, okay, and so this is for characterization of systems, okay, and we can model that. Another interesting area is doing a full analysis. So, which I know Professor Deagle is interested as well. But this is a little cartoon about one of the cartoons that we gave. So this is the cartoon, but it's has some science here. So the idea is that when water comes down onto your surface, depending on what kind of surface you have, right, the interaction is different, and you can use lights to basically break apart absorb water, okay, and the idea is to generate hydrogen, which can be done. But to model this is complicated because you really need to describe that's what the screening is. I'm going to describe what is the screening of the substrate by the substrate of the electron levels. Okay, because it's complicated to do, but this is what our method is very computationally expensive, and then depending on what system you have, right, then you have states on the side and you love and then we can also look at things like fingerprinting. And that's what my fingerprint background is. The idea is to use the eigen energies and the density of states that we calculate to try to infer what exactly they have experimentally on the surface. Okay, by seeing where the energy levels shift, and using that to say, okay, well, this is how the molecule is absorbing on the surface. Okay. In this case, what we're looking at is a catechol, which is basically the simplest knot for making movable base. It's worked on titanium dioxide. Okay. And so the idea with this is that you can actually make a solar cell which generates electricity. One simple experiment you can always do is take titanium nanoparticles and some tea, like this tea, put it in, mix it up, and put in the electrodes, and then you can have your undergraduate students or high school students or even public school students make a photovoltaic cell. Okay, it's very straightforward. Then the idea also is when you have the particle absorption process, if we can tailor what energies your molecule absorbs, okay. So you can use what energy it absorbs as a fingerprint for determining what you have experimentally in your system, right? But also if you can describe correctly the interaction with the substrate, then you get the presence of the substrate can actually cause a hybridization of the levels, and you can actually modify the absorption spectrum of a molecule when it's absorbed on the surface. And you can then use that to tailor or alter the absorption spectrum of the molecule. So one potential application of this would be that you can actually, there are some levels of potential excitations which are what they call dark. So dark excitation is just an excitation which can absorb light. But if you have a coupling to the substrate, then in the case of the polarity, you can actually turn on those dark excitons and make them bright. Okay. But that's only if you've got something like gold or silver. At least that's what the calculations show. And these are GWC level. But using a simple model for the substrate, just using its density. And we're trying to do the experiments for years from the pandemic and lots of polarities, and we've got the contacts with people that still haven't been able to do it. So yeah, I'd like to see is this real. Okay. So and then you can also think, well, you just want to know what is the actual absorption process. So here we've got the chlorophyll molecule, the basic building block of the chlorophyll. Okay. the chain is experienced a long way, but what we see is that because the excitation doesn't actually involve that long chain, it's actually occurring around the center. And so this is what's the opposite. And so trying to figure out what do we need to take into account in order to describe the absorption of these basic building blocks to all. There's also the big question is in plants you have an enormous complex of proteins and thousands of atoms, an enormous macromolecule. Why does the plant put all the effort into making these all these proteins if really the absorption is just occurring here? What is the role of this? But of course, that's very difficult to simulate to calculate with these big systems. So we need to come up with new methods which give us reasonable accuracy, quantitative accuracy, but also provide us with which is robust and highly parallelizable and very efficient, so we can then probe these aggregator systems. Okay? Because there's always a bigger system that some experimentalists like us to look at, right? So trying to push the envelope not just in terms of doing more accurate calculations, but also in terms of developing simplifying methods which give us sufficient accuracy, but are more robust and faster. Okay, that's also a big part of the work that we've been doing here in the township. Okay, yeah, this language is she's Maria Rosa, is one of them. She was the valedictorian in the first cohort of and then well, we've also got the idea of like a full photovoltaic system. So you have light coming in, you have some in this case the polymer, where the absorption process occurs. And when you have this excitation, right, you want to use that to do some work. You have always fight against what's called generation or electron hole recombination. Okay, so you generate an excited electron, and then there's a hole where the electron rusts, right? That's the hole is positive, the electron is negative, so they attract. So you have some electron hole binding, okay, and you need to somehow overcome that binding to separate the two so that they don't recombine. Okay, so that you can then take the electron of the hole off and do some work with it. So this whole process of what's the likelihood that you absorb, you excite, but then that excited electron may be transferred. So this is a model donor acceptor system. So the electron is excited on the polymer, but then the conduction band minimum, the excited energy of the polymer is higher than the conduction band minimum on the nanotube, and so the excited electron energetically is driven to jump to the nanotube. And once it's on the nanotube, nanotubes are realistic conductors, so it can be easily conducted away. I mean that was kind of an idea, but when they were trying to do this experimentally, they didn't have so much fun. Okay, but they a specific molecule. And I don't know, did you say there's a lot of different possible molecules to check. To do experiments with every single one, you need a machine, you need a robot to do that. You also need to buy every single one.
That's a good word.
Sorry,
That's a good word.
Single wall. Yeah, this is a single wall. Yeah, you could also have multi-wall nanotubes. You have all different types of hydrology is sorted. But that's good. Nanotubes is also polarized. And then there's nanoparticles, there's all kinds of different materials that you could imagine. Right? But every material should be checked. So the idea would be to do it on a computer. The computer could do it faster. And even if you don't have the exact number that you're going to get 1.3, not 1.2 EV or blah, blah. You just need to know, is it a good candidate, right? Which are the best candidates? So looking for candidate materials and then doing the experiment only on the best possibilities or what's the theory suggested to save time and everything. So okay, so now I just been showing you some cartoons, so now let's get into some actual science. So I didn't know what level I should make the talk, but I see that I've got a mixture of both older and younger audience members. People from different areas, but anyway, so I thought I'd just begin with the idea. Well, in the title I mentioned the Nanosca. Right? And so what is interesting from my perspective of the Nanosca is that there you have both quantum mechanics and plasma mechanics. Okay, applied. So the photons, the light source, the electrons, those all you need to describe at a quantum mechanical level. So they're showing that one and okay. So you have this superposition. So in the electrons, you need to be able to describe quantum mechanically to get anything near right on the scales. Because remember that the nanoscale is just maybe there's 10 atoms in a nanometer, right? So we're on the scale of individual atoms and molecules, right? Okay. But the ions themselves, those can typically be treated classically. Because their mass is so much greater than the mass in the electron. The basic idea is that the ions, by the time the ion moves a little bit, the electron is already relaxed to its ground state. Okay. Because there's a ratio of mass just for the hydrogen atom of 1,836. So you've got more than 3 orders of magnitude, and that's just for hydrogen, the smallest carbon. So you've got 4 orders of magnitude. So the ions can treat basically it's classical particles. So this is what's known as the Bohr-Oppenheimer approximation. And this is very reasonable, very accurate. Now there are some systems, there are some experiments that have shown where you need to take into account the hydrogen atom that you can flip from one location to another. When these things do occur, okay? Not saying they don't, but overall, in general, this is a very good approximation that is really important bedrock because of how we will try to model this. It allows us to decouple all the coordinates of the ions from the electrons. We can just say we treat the ions as point particles, and then we just need to deal with the electron. But our wave function is a function not just of one electron, it's a function of all the electrons in the system. And that's the big complication. Okay? Because it makes it so that you need to have all the atoms. So many data, the amount of data just doesn't necessarily just store the wave function for an oxygen atom in a little 10 by 10 angstrom box. That requires you would need to use each of the atoms, the spin of the atom, each of the atoms in a kilogram of carbon just to store that information. So you can pick it. No, it's a number. It's a number. Okay. Won't waste our time, okay? If you want to describe it for accurately, you want to include all of these interactions, what we need to do is something like quantum computing. So with quantum computing, you're actually all of these interactions between correlations between particles, you can include in quantum mechanics. So if they get a quantum mechanics, quantum computers, oh, then yeah, here can unite with the other business. Like, I don't know what we would do. Maybe. Well, or we would be out of business essentially doing something else, right? Move to a different way of doing it. But all of these approximations wouldn't be necessary if we could describe the system fully quantum mechanics. Okay. So the way that we attack this problem, because we don't have quantum computers, we is a density functional. And that basically just said that if we got an external potential, which is basically where these ions are, and with that potential ion background, then the total ground state energy of the system is some unique functional of the electron density. So this means that we can just work in terms of this electron density. And the electron density is only a function of one coordinate. And the external potential is a function of one coordinate. So now we've gone from having many coordinates, we have all of these, but more than just decisions of every atom, that it's dependent on each one of those positions, each one of them. Right? So the idea is, if one electron is here, electron is here, then electron is at another point. And then the third one is at one of those. Third one is and it grows exponentially. Okay, but this resolves all that because you just need to work in terms of the electron density, which is pretty important. And so it reduces the number of coordinates we need for one, but problem is we don't know what this thing is. Has no exact form. Well, in general, there are some coordinate systems where we do have an exact one. But someone's quite a bit, yeah. So yeah, in general, no exact form, unless specific very specific cases. But this also only provides the ground state information about the ground state of the system. Right? So, but then this DFT, this doesn't give you a mechanism. This we figured this out, but then it was like variational approach. How do you go on from this how to use it? So really, what's most important is the Kohn-Sham theory of the Kohn-Sham system. So the idea was we know that for a given electron density and a given external potential, then we have a specific ground state energy. Okay. So if the wave functions are different, it doesn't matter. If you have the same electron density and correct function, then you have the same ground state energy. So Kohn and John came up with the idea. Well, let's say that we have this fantastical imaginary system, which we now call the Kohn-Sham system, which has n non-interacting electrons. So the electrons are not interacting directly. You have this potential here. So then this different equation, this we can solve with methods for solving this very, very accurately and efficiently. So we can solve this because it's only got one coordinate, right? But you have n couple of equations. But then, okay, so then what is this V? What is this potential? This V, the Kohn-Sham effective potential is the Coulomb potential coming from the electron density. The external potential, which we said that the problem is we didn't have on this. But then there's this other functional part, this is where it's really everything that we don't know. This is what's going to be described and account for the interactions between the electrons, electron coordination, electron exchange, energy, all the principle, all of these effects. Okay, so we just take everything I don't know, we just throw it in here. Okay. The problem is we don't know this. Well, we have various approximations to it. We have methods that work in some cases, okay, that work reasonably well. But the big success for density functional theory is really just be truthful. It's based on a bit of luck. Because one of the first systems that was looked at was silicon. And in silicon, and using what's called the local density approximation, which basically says, okay, well, we treat the system as if it's only dependent on what's the electron density at the position we're at. So it's local. But if it's local, that means it's the same everywhere. So to connect that to something real, that would be the same as what we would get for a homogeneous because they had a method where they could actually get what this would be, right? But with silicon, it turned out that they had another version of this, but the exchange, I can't remember if it's the exchange was overestimated and the correlation was underestimated, vice versa, but one or the other. And those errors were large, but they canceled each other. And so the results that we got out were almost bang on, very, very good. Okay. So, I mean, density functional theory has already been built around this idea of error cancellation. So there's been a bit of fortuitous side. But it also means that when people have been trying to develop and improve the theory, they're coming up with more complicated functionals, the results tend to get worse. We did it when they were doing things in a systematic way because they were trying to improve the exchange, and in so doing, they broke the error calculation, and so then the results were worse. So you have to fix things in such a way that you didn't break the error cancellation, so that it must, and also a systematic mathematical step, following a step forward in approximating functions. That type of method, like a simple, okay, which is going to be gradient dependent, is going to be second order dependent on the fluid, blah, blah, blah. Things got worse. Okay. So, yeah. And now I think most like the most advanced functionals that people are using now are actually not true functionals. Because they're actually dependent on wave functions. So which means they're very expensive, but also means they're really throwing out here. Anyway, that was a lot to talk about it. But the idea is that you have your initial guess for the density, you put it in here. Get your potential, you solve the Schrodinger equation for independent electrons, that gives you your wave functions, and then you take the absolute square of the wave function, sum over all the ones which are occupied, that gives you a density, and then you compare that density to the previous one. If it's different, then you make a mixture of the two, and you put in a new one, and redo the process until the density application is equal to the density you get out to an uncertainty that you're comfortable. Okay. So this is what's called self-consistent procedure. This is what we do. And the other thing is that, and what you get out of it, even though this is a non-interactive theory system that you're modeling, it's still your standard has the same electron density as the fully interacting system. That will not mean that even though they have different wave functions, they both must have the same ground state energy. So as long as I reasonably good function with density, for the given external potential that you're using, then you'll get electron density and the ground state energy of the fully interacting system. Okay. But these wave functions you get have no direct connection. There's no reason to think that they're any real connection. They're called the Compton wave function because they're not of any particles. Okay. So these guys, and this is what you would use if you were trying to model like excitations. But this is all people have, so people use them. But there's no theory behind. So you're skating on pretty much. Okay. So okay. So getting back, so Raman spectroscopy, where we're shining light on a system, and then we're measuring the vibration that are being excited. And so the carbon nanotube, it has this specific vibrational mode going on, which is called a radio breathing mode, where this is going out and the energy of that RBM is specific to single wall nanos. So you can use that as a non-invasive technique to see what is the more or less relative concentration of different types of single wall carbon nanotubes you have in your sample. And this is just for single wall nanotubes. Okay, so you have the graphene sheet, and basically the idea with the carbon nanotube is start here, you have this carbon atom, and then you roll around, we match another spot here, and then you have a cylinder going along. Okay. And so then you have the experimental values, and then you have the theoretical values. And they're pretty good. And the reason that this works is because to model Raman spectroscopy, we just need to know the vibrational modes, the energies of the vibrations of the atoms. But the atoms we can treat as, right? So if I move the atom and displace each of the atoms, okay, and for each of those structures, I can then calculate what's the ground state of the electron density of the electrons, and what is then the ground state energy of the system when you've done that displacement of that atom. Okay? And then you do that for all the atoms, and you can generate what's called a Hessian matrix. You diagonalize that, and then from that it will give you the energies of the phonon modes, vibrational modes. And that is just based on the total energy, the total ground state energy of the system when we displace the atoms, which is just changing the external potential. So DFT, you're doing you have a full machinery of density functional theory behind you. So as long as you have a reasonably good exchange correlation functional, then the vibrational energies that you get should be accurate. Okay, so you don't need to worry because we're not using any wave functions for that. Okay. What we are using wave functions for would be to figure out which excitations are around the pattern. Okay. In order to do that, then you need to use look at the excitations in the process. There's a formula for doing that, which is dependent on the wave functions. But it's really looking at their symmetry, right? And so the Compton wave functions, don't think of them as being something that has no connection with the other. What I'm just saying is that those are the wave functions for a non-interacting system, which has the same electron density as the interacting system. So the symmetry and some of the spatial distribution of those wave functions could be to zeroth order more or less similar to what you have to the foliage gravity system. Okay, and it's those symmetry that we need here to know if the light is coming with polarization in this direction, then it excites excitation of that energy. Okay. And yeah, and that we can do. Okay. Okay. And what Julio did was he was actually putting potassium, intercalating potassium in his single wall carbon nanotubes, and then he was looking at how this RPM, the rate of reading mode frequency, was shifting. And so what Maria Rosa did was she did the same calculation, but charging by in the calculation. And we actually get the same step behavior. So we get something like the black and the white is the experiment, the black are calculations. And so we get actually something which it's a very complicated function. But what's going on is that you have electron density. And as you're charging, you're then filling up one of these peaks, right? And that's giving you a big shift in the energy of this radial reading. Okay, when you just start, when you okay, I'm going to put in some charge, I suddenly fill this up. That makes a big difference. Okay, so that gives you the step. And then when you get up to the next peak, then you get the density phase. This is what the density phase looks like for a 1D structure of the carbon energies. So you have these singularities, okay, which mark where the band structure is flat and one is different band structure. Okay. And so we have different transitions. This all we have is okay. And so we were able to then doing that, we were then able to connect in their experiment what exactly was the charge that they were actually getting onto their carbon nanotubes. Right, so this is allowing us to characterize. Okay. So this so the other words, so this is in preparation. On the stage, he just published just graduated was his thesis on, and so this is doing exactly the same thing. Radio reading mode part of the spectrum for election part of the single wall carbon nanotubes, and then we can break the peaks and up into different peaks to get the red line, which is giving the experiments which are live, and then we get relative intensity for different species, which allows us to characterize what kind of carbon nanotubes in this sample. And so this was a film of polyvinyl multiple and single wall carbon nanotubes. They were really stretching the change the conductivity. I saw it dropping conductivity. But getting back to the calculations, what we see is that so here calculated where the measurement are the centers, that the red line would be a perfect agreement. Our the circles are they're all basically on the black one. So there's a small shift or that's inverse centimeters. Which I understand it's not too bad. You want to do that. So that is perfect. But we can account for this by saying, well, in the experiment, they're doing their measurement in solution or in a film, right? Whereas we're calculating things in vacuum. There's no other species around, and so the constant shift by the difference in environment is quite understandable. So that all looks good. So but that's just trying to help experiments characterize what their sample is. But that's not going to get us to where we want to go, which is suggesting new experiments that they can do. Okay, so here we're looking at look a little bit at orbit houses to look at this problem of the excited states. So here we're looking at UPS is the occupied states, and GPP is people on overreaction spectroscopy. This is the unoccupied states. So this is both this is all the okay, but it's being used to then control what are the energies of the excited states. Okay, and these are different levels of theory, different theoretical methods. So you can see that the band gaps should be around the balance band signals. Okay. So you can see we're back. The PDE band gap is over by factor 2. That's half what it's supposed to be. And we're over by what one on what is the energy of the unoccupied. Okay, and that so this is methanol on TiO2. And so it isn't good enough just to get what's the then in the amount of titanium. We need to know the level alignment. So where are these levels of the molecule relative to the levels of the titanium? Because remember, what we want to do is you excite on the molecule, absorb molecule, and then you have the extended electron jump to your receptors, donor receptor. And you need to have some degree of energy difference in order to drive that process. But you also need another alignment as well. Right? The two part levels are too far away in energy across problems as well. Also, we want these energies, so something like 3.2 that's ultraviolet, that's not going to be too useful. We're only getting energy problems instead. You'd rather have something around 1.5 to get more of a solar perspective. So also iterate what is the next energy balance. So it should okay. So the different levels of there. Then with HSC, this number is pretty good. But now it shifted this guy. Good. But now it's even worse. It's too far out. Okay. What's happening with HSC, which is what he's not what it does is it applies the screening to the same something like it applies constant screening. Basically says everywhere in the unit cell we've got 4 dielectric constant of 4. That's what HSC does. And so that's good for TiO2 because the electric constant of TiO2 is about 4. That's good. So you get a good result there. But you're applying that same dielectric constant for where the methanol, the absorbed species is. And the absorbed species has a different dielectric constant. Okay. So you shift these guys too much. Okay. We want to know where they're aligned. And so G on W on what it does is it shifts the titanium now probably too high now it's forward. It means something like 3.6 electron levels. Okay, the atomic levels are low at 3.2 when thought. But the G on W on is actually we're only going to give you the electronic energy parts. But if we want to describe optical absorption, we want to look at it. Atomic levels. You want to include the interaction between that acidic electron and the other. Okay. So this guy is where the makers experiment making this should be the electron. Now it's balance good. But then we go to pulling some consistent quasi particles, then now we have an even higher gap, worse band gap, and then these methanol levels are way up. And another thing is that G naught W naught doesn't tell me where the factor is. So that didn't change in the beginning. Okay. So this method gives you a factor. And so this is the other thing with some of these advanced methods is that if you try to fully converge and do the calculations fully self-consistently and get worse results. Part of you wasting all the stuff. Okay. So you have to know when to stop. Okay. So this side works pretty good. And then this is GW naught, which is another suggestion where, okay, well, so G is the green solution, and we're trying to describe the salt energy interaction correction, the value energies. That's what this is doing. And the idea is, okay, the stream W, that's already pretty good with the GW values. We don't need to cheat to be ready for that. So we just leave it. We don't change it. We don't, when we do this consistency. And I think she's done a bit, but still it's not so good. And then, well, this is the method I came up with. So we really like this side, this is just using self-consistent one part. So the idea is that you're self-consistently calculating these quantum particle wave functions as well. So it gives you the wave functions. But I call it GW1 because we only go up to the point where we incorporated one full unit of the GW self energy credit. So this is like G1W naught, but doing it self-consistent. We do it in steps. Okay. And it happened very well with this system. But anyways, actually. I mean, I don't have time to work. It's too expensive. So to think about like actually doing something useful. Here, what I'm doing is I'm plotting all of those ion energies of all those levels and how much G naught W naught is shifting on that. Okay, that's what convergence is. So basically, you're shifting all the unoccupied levels up, and you shift all the occupied levels down. Okay, but the amount that you shift them by is dependent on how much of them of the level. What's the weight of the wave function that's inside the bulk material? Okay, and that makes sense because in the bulk in the material, that's where you're going to have the screening. Whereas in the vacuum, you're not going to have screening because it's the vacuum, you're not going to screen. And there you get another zero. So you could even estimate what this line would be, just saying, well, I know this material is dynamically constant, you can figure out what the shift could be in the bulk levels. So you're going to say that just draw a line between. Okay. And you could use this in theory to just predict what the amount would be. Okay. For the occupied levels, it's more complicated. We have two different lines, two different fits, depending on what levels are calculated, what type of levels that. Okay. But for the unoccupied levels, which are probably what we're interested in, is and we're doing everything relative to balance elements. It's good work. This is one method that you could use to take into account the fact that the screening and the shift of the ion energies is dependent on the change of the waveform. It's spatially dependent. So HSE and these types of methods, they just do the same everywhere, right? Whereas this, if you're just looking at a whole material, that's perfectly great. That's you got to sit there in the way. But if you're looking at a surface with a molecule absorbed on it, you've got that. That is the situation. Okay. And so yeah, you've got this fingerprint, and then so then with the ESE method, you can actually calculate what are the ion energies of the excitons. Okay, and so this allows you to take into account exciton binding. Okay? And what you have is you have for many systems that G0W makes the band gap really big, but then when you take BSE, it makes it smaller again, and so you end up more or less where you started with DFT, or a bit small, a bit bigger. Okay, but you end up somewhere in between because you thought this is to calculate the optical gap, right? So you're not using the electronic gap. And here we're showing the excitons. And so what we're seeing is that we're exciting the electron off of the chemical molecule, which is the dye. And the excited electron then goes to the titanium D levels of the substrate. Okay. And so what we see is you get more intensity when there's a bit closer together. Okay. But in each case, that's what's going on, is that you're exciting the electron from the dipole to the titanium levels of the titanium dioxide. And so then that makes it so it's easy to separate because they're spatially different, right, in location. But on the other hand, well, we'll talk about that. And so, yeah, getting to the other question, should I stop here? Okay, well, yeah, so, we always save the most interesting stuff for later, right? So the look at the molecules from different surfaces. And so what you see, you have this is ESE spectra for the isolated molecules. So we have some here, we got some here, here. Okay, for methanol, pterylene, and fluorines. And then you've got the different metal surfaces, which will have like the excitation density. It's going to be a different where the plasma frequencies are. It's going to be a different energies, right? Okay. And so then the idea is that you can kind of line these up, see where they're in alignment, and then maybe you'll be more interaction. So okay, so then what we did here also, this is another thing that we can do, which I saw show Rodman, but we can also do Fourier transport infrared spectroscopy. So here I'm showing the absorbent. We take 1 minus this, and then that will give you the transmittance. Okay, so this is the excitation energies with our IR magnitude. Okay. And you see this peak here is has the appropriate symmetry, starting like this. They're good excite or coupled with this excitation of the benzene in the same molecule, which is the electron density. So this is where the electron goes to the excited. So the hydrogen bonds and then these anti-bond states. And so they couldn't step out between the IR this node, this guy. Okay. Then we do the same thing for charity. Okay, it's either this, but this is allowing us to actually model quite a PIR spec. So then here's the absorbance. And so what we see for the benzene, this curve is the plasma frequency of the surface. When the plasma frequency of the surface interrupts with the benzene exciton frequency, then you get something happening here. Okay. It's more obvious here for pterylene, but it's happening at a different energy. This would be like C, not so nice materials to use. We see this that going down is that going up. So you're going from having just one excitation and you have two excitations. The plasma frequency of the substrate is synchronizing with the exciton of the molecule. And then you have two peaks, two energies which are optically active, whereas before you only had one, right? Okay, because the plasmas we're not even looking at we're looking at the excitations in the molecule which absorb electrons. Okay. So this is not definitely an effect, but cesium, I don't think you probably not 100%, right? But this guy with polar beads, we have these two peaks. This is basically what is on its own, and they're very low density. And then when you get to gold or silver, then you actually have dark excitons of the polar bead, which become active, optically active when you're absorbed on a gold or silver substrate. According to our calculations. So now we have only modeled the substrate just using the electron density, so in a very simplified way, but we can go beyond that and like get a deep calculation for the substrate. But what's maybe more important is we're including the screening of the surface directly into the SE calculations of the excitations on the model. Okay. So so this is called ESE, but not just for the molecule with the substrate. So we're getting into the, so we've been trying to find somebody to do the experiments, but the problem with these experiments is that they're looking at a very high energy range. And most optical spectroscopy does. Spectrometers that keep here, they just above and below us. They can't see the peak you want to see. Maybe you could see something here, but this is, I think, the most interesting region. And it's gold and silver. It's not that complicated to have. So now I've been showing a lot of G0W, what we see very complicated, very expensive stuff. And so what we want are something simpler. And so here we took some of the stuff that I had been doing when I was in San Sebastian with video Davidson, and we developed it into a whole code here. Which we call OCAO okay, and it uses LCA also an inner combination of atomic orbitals, so that makes it very big, and just calculates the dielectric function. Using this, so it's not so complicated. Now, so we're not doing anything self-consistent. And big thing it uses is this derivative discontinuity correction for the energy gap. And so the nice thing with this is that this is something that's completely ad initio that you can calculate, and then it tells you, okay, this is how much you can fit the energy gap. Okay. And what it does, what it's saying is, and this is where I was mentioning here, is that when the valence band and the disruption band are very different in spatial their distribution. When you add a little bit of charge and put it into the conduction band minimum, the electron density changes dramatically. Okay, because you say, okay, we're going to put electron density, but in another location. And the more separated they are, here you've got titanium. I mean, just in titanium dioxide, the valence band maximum is all on oxygen, and the conduction band is independent, it's all on ability here. So you're stripping two different atomic sets. Okay? So it's not just bonding versions of the same wave function. It's a state on one species to a state on another species. So you're having a very big change in the electron density, and this is what they call this discontinuity. Okay, in the electron density. And in the derivative of the electron density. So this is where this theory comes from. And there is a nice little functional which has an analytic expression for what this delta from the exchange would be. And so it's completely abelian. We just need to do a regular PFT calculation and then take the electron density in one step and we get this number. And then we can use that to shift the items. But of course, this doesn't solve the problem I was going on about, where you have spatial the shift of the change in the electron the eigenspace inside the titanium is much larger than the shift that you need to do for states out in the vacuum, like the spatial dependence. So all this stuff is just the shift, the straight shift. This is what we call scissors operator. Okay, but it's fully application. We're not bringing in. We're not just having okay, now when you do an experiment, tell us what that number is supposed to be, and then she gives us the number. What are we doing, right? We want to help her, not her. So there's at least it's going to be an application. Okay. So. And yeah, so we got this, it's pretty available on this. A lot of uses sterilization and also issues things like the polarizability, conductivity, the two-point exciton density, these densities, these ways of visualizing the electron mole distribution are nice, useful because they're really understanding what's going on in the okay. So here, what we've been doing there is Nanosca. We've been, this is the name of the cluster. This is what the cluster looked like in the first months, just in the lab. Okay, sitting on the computer. And we have 34 results on most data squad coordinates with 32 data types around, like we achieve force, and we've got a way to get connect switch. So, but we can do parallelization for all of those nodes. And the nice thing about the machine is we're not competing with many other people. It's just and so except at the end of the semester when the students are all doing their teaching last own projects and trying to get their last calculations done before they leave, it's fun. So yeah. It allows us to test things without having to worry about that week of computer time I use we have to take it.
Okay. Sorry. We have this place on this one. Are you?
I can do it, I can stop now. But I can.
No, you got I think.
Okay, I think I'll go.
We have still 15 minutes.
Yeah.
Then we can go for whatever you want, and then sort of the questions before in order to have a question, right?
Yeah, sorry. So I'm looking at work, and then looking at what is the importance of this, and so depending what is this guy do? And what we see with the spectrum is you have a little bit of a change, but not too much. So those extra change doesn't do very much, right? And here we're comparing our code, the LCO to omega, with plane wave the idea, and you get basically the same, very close. With plane wave methods, okay? Which is to be somewhat expected. And then we also did calculations with full time independent time propagation here. And here are the experiments. Very experiments. We're able to get really agreement. with this very basic model. So it seems to be getting the physics. And it's also allowing us to automate big systems, which we're having much more problem. So here we have the dimer. Right, it's working okay. Then this is the gas line is the time propagation, and it wants to make that. The middle East is that. Okay.
Okay.
But here, what we want to do for future work is actually look at what the fact could be all. And in that case, it'll be impossible to use any of these methods. It's still very difficult to use our method. Because we need to get all that condensed. So that's one thing. Here we're looking at I'm looking at C60 again, and here you go the VSC excitation, and then what we get from our code, and quite reasonable qualitative agreement.
Okay.
We also
wait.
the many methods. We don't have like here that's the green line. But these ones actually, you know, not be a seat, it's also the strength of these means that these are actually stronger than whereas these say weaker. Okay, so there is an issue, but also in a plot, unlike 90, 95, 98% of papers, they just have arbitrary units. These are all in physical units, so these intensities are all the actual intensity. Because the basics that need actual is the benchmark or the method is there with nothing else. And then here there's the carbon dioxide. And so the experiment making all these images experiment has and where you can see what those look like and what the excitations look like. And again, we're able to get this is here we're actually showing the absolute value of conductivity. So you can see that when G0 is actually giving you much stronger conductivity closer to but yeah, I mean, using this these guys, this method. So we have two different methods. We have a method where we apply the shift a priori, the scissors operator or posterior. And so in this case, we find posterior, we get very good even for the consensus. These are all absolute intensities. And nice to be that what the expectations would look like at that energy. Yeah, I already know that. So then to understand what's going on a little bit, because yeah, we submitted that paper and then they said this is PRP, it means an explain phase. Okay, we're going to explain phase. What we see is that derivative response interaction is directly correlated with the inverse dielectric constant of the demand. So it's actually using, so that value that we're getting is actually giving you a connection to the actual screening of the material. And so what's happening is that you're at the G0W level, you're stretching the gap out, but then there's a screening from the environment that brings it back down to get to the optical depth, which is what we're trying to look for. Okay. And so, yeah, we did a couple of bits to see what is the best correction, right? And actually, you know, things out to a bit less than the actual delta X would be the best. I would see. And it's also like 1.7 times the diameter constant. That's what you need in order to do the correction for these tests. But here we're showing now here, these aren't the coordinates. Here I stretched those. But you saw they're not too bad. But yeah, we see the just a small energy shift by 2.3 dB. Actually, we're a bit higher in energy. Okay, but this is the whole 2000 population, so it would get pretty good. And also our LCA which is much faster than plane wave. It's going to be able to say, you know, it's not so many difference. So there's no thing to do with those full head of propagations. Which are impossible for these big systems. So here are the experiments, are the filling curves for the here's optical absorption, and here are the electromagnetic loss factor. And you can see that we're getting the right shape, and we're actually getting the right relative intensity more or less too. Okay? This is not the absolute scale, but I'm looking at how these compare in size. And yeah, you can see that using this actually we get more or less pretty good. The E11 transition. But for the second transition, we get actually even better. Okay. So we're able to get both of those transitions quite well in the carbon atom. The diagonal singularities. And so now we have this idea of okay, counting thought itself to be able to the difference. What do we get? So here we're looking at this all of that. And what we want to know is if we excite an electron in the polymer, just go out the signal and what you see is that you have the excitation is red, the hole is red, it's mostly on the polymer, and the excited electron is going to jump to either the carbon nanotube or the PCM. Okay, and the difference is 5.1 of the electron. And this is electron hole separation. This is what we would like to get about. Because this would make things this would make things more efficient. And so here we did the same thing with the fluorine, and you can see that the electron is mostly on the fluorines, and the hole is mostly on the polymer. And we see the same thing in the carbon nanotube with different charge transfer grids and but at the same time, the electron is still in the vicinity of the polymer. Okay. And Barrios did some further work, which I haven't shown here, and I let a new student is doing some experiments combining the chlorophyll with the carbon nanotube. And he told me last week, he said when she excites in the chlorophyll, actually the electron wants to go away on the carbon nanotube. Once it's over here, it's farther away, which is very interesting. That suggests there's a big driving force for and so yeah, then what we did was we actually calculated the transmission through, and then depending on the filling, and then you have different transmission probabilities, and so this is what interesting. I'm giving you the so now this is the final, this is the future work, this is what we're working on and by Jason and Dana. Yeah, we're the students here, and they're teaching math 1 and 2 those projects. And so what we wanted to know is, can we now combine this transmission with non-equilibrium Green's function method to get how the electron, the probability of an electron going through the system, and that's what that gives us. Can we combine it with a description of the absorption process, like we found was very effective with the LCO2. Okay, and so what we're doing is we're saying, okay, we have an electron going in, And then it enters this interfacial region, and there's a donor and acceptor. And then we apply this information to the Hamiltonian that we have a vector potential coming from an external photon field, right? We've got this bit of momentum, and then jumping up into a higher energy unoccupied state. And then you potentially couple with some photon change your level again, and then you have another energy class. And this is what we're working on right now. And we're using just this very simple type binding point model, and already just with that simple model, we're getting some structure. It's something, so what's interesting, what we're getting, I'm just getting a straight flat line. So this is where our future work is. But I thought all of this, I think I mentioned again, and listen to some questions, but yeah, there's students who are interested. There's a lot of things.
I'm so sorry to interrupt you. We have a class coming. And I just wanted to say that really is a privilege to hear the person that you very, very nice and you're talk. Really privileged to hear you in our time. I hope that people who are interested in the field have the opportunity to talk. I think you will. But we can make it, we can have it. I will talk to you. There are so many forms involved there. But I want to know if you have any questions, please, in these 5 minutes, please.
Well, yeah, a lot of questions, but yeah, thank you very much. And do you know, actually, the second interaction error is very famous immediately. And do you know about for atoms which are heavier, there is this DFT plus U technique.
Yeah.
Kind of like it's also in the case of carbon molecules or things like this.
Yes.
And
But I don't know if I've never done it.
okay.
And I don't know if it works. In the group that I was in, we were not so kind of advanced with that because what is the value of U? Well, it's basically the same as in the scissors because you have to decide, well, what are you going to do? The thing I like about this derivative discontinuity correction is it's something to do with navigation. There's math behind it, and we can calculate it, and we're not just doing an interpretation. Not that there's anything wrong with getting it's, but probably don't play. That's I think the disadvantage of DFT plus U, but DFT plus U can solve all of these problems because what you do, I guess, will do the case with the reference. That's another.
And the process exactly the question of the exchange. NDFT in general, well, yeah, the exchange is not perfect. But from the molecular level, this super popular with radio, where they are using the part of the exchange from Africa. So can we do it something like this also from Africa, or is not possible to the exchange from Africa, or to put it inside the at least the powers?
But isn't that more or less it's a little bit simpler version of G.W. I mean, that's kind of what GW is doing as well.
You are also in the market,
But I hope you have the dialogue. Appreciate that. I'm sure you will have. If you have a question, he's in your department. And later on, we have to make questions. It's already this is the beauty what we have today. I'm very impressed. Gracias a los amigos en vivo, de 9 personas que por